Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So, till now we have completed in our ray optics chapter. The topics reflection of light is completed, then spherical mirrors completed, mirrors formula also completed, and we are moving with refraction of light. In that the topic reflection of light, we have covered so many things like refraction, laws of refraction, okay, and the refractive index and cause of refraction. The speed of light is different in the different mediums, as wavelength is also different in different medium. Hmm. And absolute refractive index and relative refractive index. Clear? Okay. Before going on, we revise the principle of reversibility. In last class, I said that uh, the refractive index of one medium with respect to another medium, like if a light is moving from one medium to the another, this is a medium one. So if a light ray is coming like this and moving to the second medium, this is medium number one and this is medium number two. So first refractive index, this is equals to mu 1 2 equals to sine I upon sine r, and another refractive index, so here it is equals to sine I upon sine r. Clear or not clear? This angle is angle of incidence I. It is refraction angle of refraction r. So mu 1 equals to sine A upon sine r. If you reverse the path of this light, this means the refractive index of the first medium, sorry, here the refractive index of second medium with respect to first medium. Now here the refractive index of first medium with respect to second medium. Okay. So here it will be mu to 1 because the light is coming from 2 to 1. Clear? So this equals to sine r upon sine I, two relations. Now if you 1 multiplied by 2, you will have mu 1 2 into mu 2 1 equals to sine I upon sine r multiplied with sine r upon sine I. Clear or not? They get cancelled out and you can write mu 1 2 into mu 2 1 equals to 1. Mu 1 2 into mu 2 1 equals to 1 means mu 2 1 equals to 1 upon 1 mu 2. Clear or not clear? This concept is called principle of reciprocity. This is called principle of reciprocity. Okay. Principle of reversibility, not reciprocity. Reversibility. The principle of reversibility of light states that when a final path of the light ray, after suffering any number of reflections, are reversed, then the ray retraces its own path exactly. It means there are so many type of times of reflections takes place, and finally when you have placed a plane mirror in the path of a refracted light, so the same path will be retraced. Clear? So n21 into n12 equals to 1. This is called law of refraction, principle of reversibility. Clear? Okay. Now, next very important topic of today's class, refraction of light through a rectangular glass slab. So kindly make of this diagram to understand the concept of refraction of light through a rectangular glass slab. Students, here we have a rectangular glass slab. Okay. And the incident light ray coming with an angle I1 here. Okay. Making an angle I1. Then what happened? Uh, from rarer to denser medium, because outside medium is air and the light is presenting inside the glass, so medium is rarer to denser. The refracted light is refracted moving towards the normal and having an angle r1. This angle is r1, then definitely this angle will be I1 minus r1, because this angle whole is behave like a I1 and this smaller angle r1 is subtracted, so the remaining angle is I1 minus r1. Got it? Yes, so this angle equals to I1 minus R1. Finally, the reflected ray incident on this second interface and making an angle I2. Yes, this ray inserted on angle I2. This angle is equals to I2. Clear? And your final angle, again, it is deviated away from the normal and make it an angle R2. Yes. So what is the direction of incident ray? These dotted line referring the direction of the incident ray. So you see what is the exactly between the incident ray and refracted ray. There is a gap between incident ray and refracted ray. Clear or not clear? Yes. The incident ray, the direction of incident ray is this one, and exactly the light is somehow you can say laterally dispersed, laterally deviated, okay, from the direction of incident ray. This displacement is called lateral displacement. Yes, this distance KL dash is called lateral displacement, and here we have to find the amount of lateral displacement. Got it? Yes, we have to find this distance, lateral displacement. So how to find this lateral displacement? Once again, try to understand what happening here. There is a glass slab. First, you have a glass slab of any thickness. Suppose the glass slab thickness equals to T. Okay. Incident ray incidented on some angle. Say this angle equals to I. Then the direction of incident ray is like this. It has to be like this. This is the true direction of incident ray. Now, after the refraction, the refracted ray is like this. And then again, the refracted ray, you can say this is emergent ray. Emergent ray. You see, it is clearly parallel to the direction of incident ray. And what happened actually, you have got a slight displacement between the original ray and the emergent ray. This displacement is called what? Lateral displacement. Okay. So you have to find this lateral displacement. Okay. So what is lateral displacement? Perpendicular distance between the incident ray and emergent ray. So the perpendicular distance, yes, the green one distance. This is what? This is your incident ray and this is emergent ray. So this distance is called lateral displacement. It is called KL dash. The perpendicular distance between the incident ray and the emergent ray is called the lateral displacement. Clear or not? So you have to find actually here KL dash. I can suppose this one as distance by x. So how you have to find this displacement KL dash? This angle is theta. If this angle is theta, this work is 90 degree, right triangle. Now sine theta is equals to perpendicular upon hypotenuse. So this angle equal to sine I1 minus R1 equal to perpendicular become KL dash. Hypotenuse is the opposite side of this angle. So this become NK. Clear or not? Okay. So sine theta is equal to perpendicular upon hypotenuse. KL dash upon NK. Now, to find this distance NK, okay, to find this distance NK, you have to use a triangle N and SK. Yeah, this one triangle, the blue one. I can take this one as the blue one, N and SK. Okay. What to find? To find this NK. Okay. So in this triangle, take cos theta. So cos R1 is equals to base upon hypotenuse. For this angle, base is equals to this N and S, and hypotenuse becomes what? This NK. Now, N dash is what? It is the thickness of the glass slab. So N dash becomes T. So you can write cos R1 equals to T upon NK. Clear or not clear? T upon Nk. So make Nk upside. So Nk is equals to T upon cos R1. So now this is Nk. Nk equals to T upon cos R1. Now again move to the equation number A. Yes, what is equation number A? Equation number A is equals to sine I1 minus R1. Sine of I1 minus R1 is equals to sine I1 minus R1 equal to KL dash upon NK. KL dash lateral displacement upon NK. Okay. You can replace uh, KL dash as X. As I said that KL dash is the lateral displacement which is equals to X. Okay. So you can place a X there. No problem at all. So KL dash NK. So KL dash that is equals to NK sine of sorry I NK sine of I1 minus R1. Clear? Now place the value of Nk. What we have got the value of Nk. Nk is equals to T upon cos R1. So you can place here t upon cos r1. So t upon cos r1 into sine of I1 minus r1. Got it clear? So this is the expression for lateral displacement. So x equal to t upon cos r1 sine I1 minus r1. Okay, done. Next concept, students, apparent depth and normal shift. Okay, so what is apparent depth? So maybe in some practical situation, we have found that when we drop a coin inside any liquid bucket or something, if you have dropped some coin, so it is looked somehow upward from the surface, from the bottom surface. Yes or no? So this is actual height h, and this is apparent actual depth actually. If the water is filled up to the rim, then this is the actual depth of the coin, and this is apparent depth of the coin, h dash. Actually, relation to be learned is h dash equals to h upon mu. Mu is the refractive index of the water or liquid in which you displaced, in which you inserted your coin or something. So we have to find this apparent depth by the derivation, apparent depth and normal shift. Yes. So question is, what is apparent depth? So when an object is in denser medium and observer in the rarer medium. So here is your observer. The observer is in rarer medium. Okay. So this is your observer. He is in rarer medium, and he put some coin inside a liquid. The actual depth of the liquid is d. The object appears to be some lesser depth. Yes, the object is appear to be lesser depth than its actual depth. Yes. So you have to find its apparent depth. Now, how the refraction takes place? First, see. First, see, this is the object. So first ray that is directly going upward from the coin, that will suffer no refraction and will be directed in the straight path. Okay, because in the condition of normal, there is no refraction. Okay, so if the ray is coming perpendicular to the interface medium, so there will be no refraction. This is first thing. Now when the second ray is intersecting, when the second ray is coming, now if this angle is, yes, when the second ray is coming, then what happened? The rays is coming from denser to rarer, so it will bend away from the normal. Okay, bends away from the normal. Now if you move the refracted ray in the previous direction, you will have its virtual image, that is called I. So actually your coin is at place O, but its virtual image will be seen at point I. That is your virtual coin. So this is your real depth, and this will become your apparent depth d dash. Okay, so you have to find this apparent depth d dash or AI. Okay, so apply the formula. This is the first medium, and this one is the second medium. So by the Snell's law, n to 1, the refractive index of second medium with respect to first medium. Now refractive index of second medium with respect to first medium. So if this angle is I, this angle is R. So n to 1 equals to sine I upon sine R. Yes. N to 1. Refractive index of second medium equals upon first medium with respect to first medium equal to sine I upon sine R. As sine I equals to tan I. Why this consideration has been taken? Because in the optics, sine I for a small angle. Yes, note this point. It will, so many times this concept will come. For a small angles, for small angles, sine theta is near about to theta. Tan theta is also approximated to theta. So sine theta equals to tan theta, and both these values approaching to theta. Yes, write this point, make this point. So sine theta is equals to tan theta is equals to theta. Clear? Hmm. So the sine of angle of incidence equals to tan of angle of incidence. Sine theta is equals to tan theta by the consideration. Then tan theta, this one angle, check this one angle. Tan theta is equal to perpendicular upon base. So perpendicular here is AB, side opposite to the angle is called perpendicular, and base is here AI. Okay. So tan theta is equals to AB upon AI. This is what this is becomes sine I. Now cos sine r. Sine r is also equal to tan r. So sine r equals to perpendicular upon base. Perpendicular is again AB and base is AO. Yes, this base is the larger side, that is AO. Now place the value of n21. N21 is equals to N21 is equals to refractive index of second medium with respect to first medium. Yes, N21, it is also called 1 mu 2. In the place of N21 is equals to 1 mu 2 equals to sine I upon sine R. Sine R. We have found the value of sine I as what? Sine I we have calculated as AB upon AI. AB upon AI. So this is equals to AB upon AI, right? And sine R is equals to AB upon AO. AB and AB get cancelled out. So 1 mu 2, 1 mu 2. This is equals to what? AO upon AI. Clear? So it is equals to AO upon AI. 1 mu 2. Check here. The above medium is air and second medium is liquid, some water or anything. So when a light ray is coming from air to water, then the refractive index, relative refractive index is called as absolute refractive index. So here in the if the first medium is air, then you can write 1 mu 2 is equals to mu. Yes or no? 1 mu 2 is equals to mu. What mu water or mu liquid? That is absolute refractive index. Clear or not? Yes. As the first medium is here air, so you can write here, this is the medium refractive index as mu. Okay. So mu is equals to AO upon AI. What is mu equals to AO upon AI? Now place the value of AO and AI. What is AO? This is apparent depth, D dash. Okay. And what is AO? AI is the apparent depth, D dash, and AO is the real depth, D. So AO mu equals to AO is the real depth D and AI is the apparent depth D dash. Clear or not? In some of the books, it is also considered as real depth is H and apparent depth is H dash. So D dash equal to apparent depth is equals to what? D by mu. Or you can say H dash equals to H by mu. Clear? So this is the definition, difference between apparent depth and real depth. Yes. Now, the normal shift, actually, what amount of shift is taken here? You check the shift is from O to I. Yes. What is the shift here? Actually, your object is presented at O, but your actual virtual object is presented at I. So actually, what is shift? Shift is taken from O to I. So you have to find OI. So what is OI? Normal shift OI is equals to AO minus AI. Agree or not agree? The shift is here AO, A to O minus A to I. That is said to be AI. So what is AO? AO is the actual depth D. And what is AI? It is the apparent depth D dash. So D minus D upon mu. We just have calculated D minus D upon mu. In the case of place of D, and you can also take mu, that is absolute refractive index. So D1 minus 1 upon mu. This is called what? This is called normal shift. Clear? Okay, once again, so normal shift equals to, what is the normal shift? This equals to AO minus AI. Okay, means Your image, your object is here, that is a o, and virtual image is here I. So this position, this variation is called normal shift AO minus AI. So this is equals to d minus d dash, d minus d by mu, because we got d dash as d minus mu over d upon mu. D taken is common, 1 minus 1 by mu. Now write all the things. Okay, students. So refraction part of the this chapter is totally completed. Now our next topic is total internal reflection and optical fibers. So total internal reflection is an optical phenomenon. How it takes place? See, as you know, a student, when a light ray is coming from denser to rarer, like this medium is, sorry, rarer to denser, it is bending towards the normal. Okay. And when a light ray is coming from denser to rarer, then what happened, beta? It bends away from the normal. Okay or not? When it coming from denser to rarer, it bends away from the normal. Clear or not clear? Now check here. Take a situation here. This is the interface, medium interface, and this is normal. And now this medium is denser, and the above one is rarer. A light ray is coming like this. It bends away from the normal when it is coming from denser to rarer. First, the situation is like this. So light ray incidented here from denser and bends away from the normal. So it goes like this. Okay, clear? Now you increase the angle of incidence. Check. First, the previously the angle of incidence were the less one, that is theta 1, and now the angle of incidence is the greater one, that is theta 2. Now, if you have increased the angle of incidence, then light ray more and more getting away from the normal. You check the if the light ray incidented on the more angle, it will be refract on the more angle. Clear or not? Now, on continuously increasing the angle, a situation came like if the third ray having a more angle of incidence, so it get aligned to the interface medium, and here the refraction angle equals to 90 degree. Clear or not? So R equals to 90 degree. Yes. So the angle of incidence for that angle of refraction equals to 90 degree is called critical angle. So this time your angle of incidence theta 3, the third angle theta is called critical angle. I am making a clear diagram to make it more understand. Yes. See here the incident ray incidented with some particular angle IC, and the refracted angle becomes equals to 90 degree. Clear? So I equals to IC. The angle of incident for that refraction angle becomes 90 degree. This angle is called critical angle. Okay. This angle is called critical angle. Yes. So make out derivation related to the critical angle. Yes, this is medium number 1. This is medium number 2. This is rarer, denser medium, and this is rarer medium. Clear? So 1 mu 2 equal to 1 mu 2 equals to sine I upon sine R. Clear beta? 1 mu 2 is equals to sine R, sine I upon sine R. Medium 1 and medium 2. Medium 1 is denser here and medium 2 is rarer here. So 1 mu 2 equals to sine upon sine R. In the place of sine, there is IC, sine IC, and sine R equals to what? 90 degree. Clear? Yes. If your second medium is some medium mu 2, that is some refractive index, actually second medium has to be the rarer medium. So mu 2, this is equals to mu of air, that is equals to 1, and mu 1 equals to some medium, that is equals to mu medium, because it is the denser one. Now coming to the main formula, 1 mu 2, this is equals to mu 2 upon mu 1, equals to sine IC upon sine R. Sine 90 becomes 1. So check here, mu 2 is equals to medium of the second medium, that is here air. So mu 2 for air is equals to mu 1, and mu 1 becomes mu, that equals to sine IC. Okay. So sine IC equals to 1 upon mu. Sine IC equals to 1 upon mu. Clear? Hmm. Write this one. Sine IC equals to 1 upon mu. What is mu? Mu is the refractive index of, absolute refractive index of the denser medium. So mainly definition is the angle of incidence at which the angle of refraction becomes 90 degree is called critical angle. The value of angle of incidence for that angle of refraction becomes 90 degree is called critical angle. Clear? Okay. So till now you have seen, okay. Write one more line. If sine IC equals to 1 upon mu, so mu is equals to 1 upon sine IC. A numerical may be there. Mu equals to 1 upon sine IC. Refractive index of the denser medium is equals to 1 upon sine of critical angle. Yes. So you seen that when a light ray incidented at angle of critical angle IC, then your refracted light is aligning the interface and getting an angle of 90 degree as an angle of refraction. Now consider, if you increase your angle of incidence, then critical angle means your angle of incidence I is greater than IC. Now when your I is equal to IC, your refraction angle of refraction becomes 90 degree. But your angle is greater than IC, then your refraction angle would be greater than 90 degree exactly. And the light will reflected back into the same medium. This refraction is called TIR, totally internally reflection. This is called total internal reflection. So this thing we have to study today. Total internal reflection. When a light ray traveling from denser medium towards a rarer medium and it is incident at an interface with an angle of incidence greater than the critical angle, then light ray is totally internally reflected back into the denser medium. This phenomenon is called total internal reflection, TIR. Yes. So check here with the diagram. Here some angle I, angle of incidence is less. So what the refraction is like this. Okay. Refraction part is like this. Now, if you increase the angle of incidence I, the refracted, the angle of refraction is increases and the refracted like this. Now, when you increase the angle at an angle of IC, this means critical angle, your refracted ray is aligning on the interface, but your angle of incidence is greater than IC. So your reflected ray gets back into the same medium from where it is incidented, and this is called totally reflected ray, and this is called total internal reflection. Clear or not clear? Yes. Critical angle. We just read that the angle of incidence in a denser medium for which the angle of refraction of rarer medium becomes 90 degree is called critical angle. That is I equals to C. The angle of the value of incidence angles becomes C when R equals to 90 degree. So mu rarer upon mu denser, and just I think we have completed sine C equals to mu R by mu D. In this all we have completed here. No need to write it again. Mu equal to sine C. Clear or not? Yes. So same thing, mu equal to 1 upon sine IC. Mu is equals to 1 upon sine IC. So sine IC equals to 1 upon mu. So sine IC equals to, now sine get transpose this side. It will become sine inverse 1 upon mu. Okay, only mathematical type of written here. Some C equals to sine inverse 1 upon mu. Clear? Okay, student, a numerical is here from real depth and apparent depth. For air and water, A mu W means refractive index of water is equals to 4 by 3. So, as we know, we have the formula that H dash equals to H by mu. Now, if you dipped some coin in the water, okay, so this is the coin in water. Now, what will be the this coin is dipped at a depth of liquid of height h. Now, what is the apparent depth of this one coin h dash? So, as we know, the refractive index of water is equals to 4 by 3. Refractive index of water equal to 4 by 3. So, h dash equal to h divided by 4 by 3 in the case of water. So, this will become 3 by 4th of h. Yes. So, the same thing is said here, like for air and water, A mu W equal to 4 by 3. So, I apparent is equals to 3 by 4th of OA. What does it mean? I apparent, it is nothing but H dash equals to 3 by 4th of H, means 75%. Clear? 3 by 4 of the real depth of the tank of water. So what I said, H dash equals to 3 by 4 of H. Same thing was told here. Totally internal reflection we have seen. Yes, all the things are completed here related to totally internally reflection. Now, what are the essential condition for totally internally reflection? First condition, the light should be travel from a denser medium to a rarer medium. First thing. Second, angle of incidence of denser medium should be greater than the critical angle. Yes, angle of incidence in the denser medium should be greater than the critical angle for the pair of media in the contact. Yes, we have also completed critical angle. All the things we have completed and derived the derivation. A mu b is equals to 1 upon sine c. Okay. Now, one important thing here, it is application of total internal reflection. So, total internal reflection applications are very important. Yes, so first see the value of critical angle. Then after I can apply the concept of total internal reflection. First see, condition must be for TIR. For total internal reflection, the ray must be travel from denser medium to the rarer medium. First thing. Second, the angle of incident must be greater than the critical angle. Angle of incidence must be greater than the angle of critical angle. Clear. Now check for water. Water refractive index equal to 1.33, and by the formula C is equals to 1 upon mu sine of C equals to sine inverse 1 upon mu. You get that angle 48.75. Clear? Means for water air interface, air water interface, the angle of the critical angle is 48 degree. It means if any ray incident on the water surface from denser medium with an angle of greater than 48.75, then there will be no reflection will takes place, refraction will takes place, only total internal reflection. Why? Because critical angle is 48.75, and when your angle of incidence is greater than critical angle, then total internal reflection will be there. Clear or not clear? For crown glass, the value of C is equals to 41.14. For dense flint glass, it is 37.31. And for diamond, it is very less, 24.41 degree. Clear or not? So for diamond, critical angle is very less, very short angle, very small angle for critical angle in the case of diamond. Clear? Yes. So what happened? This is the reason behind the case of brilliance of diamond. Yes, the critical angle is here of only 24.4 degree. This means any ray that is having an angle greater than 24.4 means if the angle is becomes 25 degree, then the rays will not refracted to the another medium. Rather, it reflected back into the same medium. Okay, so in the case of diamond, the cutting of the diamond made so that everywhere here is TIR means light ray get totally internally reflected here. Again, it is totally internally reflected here. Again, it will totally internally reflected here. Means everywhere the light getting okay thrown out from one face to the another face, from one place to the another place. Clear or not clear? So light will enter once, but it is very difficult for the light to get refracted and get outside. Okay, getting out. So the light will strike from one area to the another area. So because of very small totally internally reflection, and the diamond will sparkle. Clear? So diamond is cut suitably so that the light entering the diamond from any face falls at an angle greater than 24.4 degree. Therefore, it suffers multiple total internal reflections. So many times of internal reflection was there. Okay, at various spaces and remain within the diamond. So the light will remain in the diamond. Why? Everywhere it get it internally reflected and not able to come outside. Okay, so the diamond and does not come out has a diamond sparkle. Clear or not? Yes. Next case is mirage is out of the syllabus. Totally reflecting prism. Yes. Now see the totally reflecting prism. How you can take the advantages of the totally reflecting prism glass prism. What are totally reflecting prism? Actually, it is a technique to get the uh, deviation of 90 degree of the light ray or 180 degree of the light ray. See here, what does it mean? What I want to say, like here it is your incident ray, clear or not? And you want to make your light going like this. This means there is a 90-degree reflection. Yes or no? 90-degree deviation. Clear? 90-degree deviation. So this can be carried with the help of totally reflected prism, that using the idea of total internal reflection. One more thing, if incident ray is like this and you want to make this light going like this, then how much angle of deviation is here? Here it is totally 180 degree of deviation. How? This is first 90 degree and this is another 90 degree. So total 180 degree of deviation is there. So this also can be carried out by the totally reflecting glass prism. Okay. So what are totally reflecting glass prism? These are the right angled prism which turn the light through 90 degree or 180 degree. They are based on the phenomenon of total internal reflection of the light. Hmm. Mu for glass is 1.5. So that the critical angle for the glass interface is 42 degree. Yes, means critical angle is 42 degree. Now see, this is the your object AB, and your incident ray is getting on this face such that your incidence angle equals to 45 degree. Now tell me, 45 degree is greater than 42 degree. Say yes or no. Obviously it is 45 degrees greater than 42 degree, and your 42 degree is greater than critical angle. So when your incident angle is greater than critical angle, then reflection will takes place and the light ray reflected like this. Clear or not clear? So this is the image of A, that will be A dash. Similarly, from the rays coming from the B are totally internally reflected and they getting the reflection like A dash B dash. This is B dash. Clear or not clear? Now check how much degree of deviation is there. 45, 90 degree. Clear? Like initially your object is like here. This is B and this is A. And now it has become like this B dash A dash. So how much angle is traveled here? Totally 90-degree angle. So this is called totally reflecting prism. Clear or not clear? Yes. So in totally reflecting prism, glass prism, angle of incidence is made 45 degree, which is greater than the critical angle of the glass air interface. Hence the light suffers total internal reflection. Now check here the deviation is 90 degree, and now here I am taking the deviation of 180 degree. How? This is the first ray that is coming from A, totally internally reflected and goes here. And again, this ray is totally internally reflected and goes here. This is the incident ray, again 90-degree deviation here and 90-degree deviation here. So do you feel here how much angle of deviation is taken place? 180 degree. Okay. Again, the light ray that is coming from B to incidented at an angle 45 degree, that is greater than 42 degree. Now this ray totally reflected here, and again here the angle of incidence equals to 45 degree, which is greater than 42 degree, and light ray totally internally reflected here. Clear or not? Yes. So total angle equals to how much? 180 degree. Why? Because you see, the first your object is in the direction of AB, point B is downward and point A is upward. But in the reflected ray, B dash is here and A dash is here. So total a 180 degree of deflection will takes place. Clear? Now, next importance of this phenomenon equals to is what? Optical fibers. Now, what are optical fibers? Today, in modern communication technology, we using fiber internet cables inside the land, which are used to connect, used to travel, used to travel high speed internet signals. Okay, why? Because light is traveling in the speed of 3 into 10 ki power 8 meter per second. That is quite high. So these cables, fiber cables are used to for communication purpose. So optical fibers consist of several thousand of very long fine quality fibers of glass or quartz. Glass or quartz means two type of material may be taken there, either glass material or quartz material. Of the diameter of each fiber is of the order of 10 to the power minus 4 centimeter. Yes, this is the diameter of the quartz cables with refractive index of the material is about 1.5. Yes, the central material having refractive index equals to 1.5. Clear? The fibers are coated with a thin layer of material of lower refractive index of order 1.48. Yes. Try to understand there are two types of materials. First, inner side material is of glass that having refractive index of 1.4, and outer side it is coating that is called cladding, and this cladding having a refractive index of 1.48. Clear or not clear? So you check that the internal refractive index is less of 1.4 and the outside refractive index is high, that is 1.48. So when a light ray mm, wait, sorry, it is inside it is 1.5, sorry, inside the refractive index is 1.5, not 1.4. It is 1.5 and the outside it is of 1.48. Fine. So when the light ray is incidented here, first it is reflected from the 1.5 refractive index to 1.48. This means denser medium to the rarer medium, and it is totally internally reflected. Again, it is reflected from 1.5, that is the glass quartz refractive index, to 1.48, that is what our cladding refractive index. So again it is totally internally reflected and the same phenomenon is continued up to a long distance, and finally by the using of total internal reflection your signal getting out. Clear? So the fibers are fabricated with a high quality composite glasses, quartz fibers. Each fiber consists of a core end and cladding such that the refractive index of core is higher, that is 1.5, that of the cladding, that is 1.48. When a signal in the form of light is directed at one end of the fiber at a suitable angle, it undergo repeated total internal reflection along the length of the fiber and finally comes out from the other end. Thus, these exist extensively used for transmitting audio and video signals through long distances. Yes, these cables are used for transmission. Okay. So what is happening here? This is the light ray. Now this is totally internally reflected. Again here it is totally internally reflected because it is refracted from a medium of 1.5 to 1.48. 1.48 is the refractive index of cladding and 1.5 is the refractive index of the quartz material. Clear? Again it is reflected back, again and again it is reflected, and finally it getting outside. Clear, beta? Yes. So application of optical fibers are very common. Okay. Yes. And this is total. This is core. The central part is called core. This is cladding, the outer material of the outer coating of the quartz material, and this is plastic cover. Maybe somewhere you have seen the optical fiber when the construction work is uh, going there during roadside construction of optical fiber installation. That time you may seen that. Yes, light ray incident on the one end of the fiber at any small angles enters the fiber after refraction and undergo repeated total internal reflection inside the fiber. It finally comes out of the fiber at the other end, even if the fiber is bent. Yes. Now check. This is very useful and very durable. Why? Even fiber is twisted, okay, or bent. Actually this reflection is taken places at very small area, so there is no impact of twisting it or bending it. These cables are very durable, okay. Even the fiber is bent or twisted in the form, and there is almost no loss of light through the sides of the fiber. Clear? Next is application of the optical fibers. Optical fibers are used for transmission and reception of the electrical signal by converting them first into the light signal. Okay, so light signal may be transmitted from optical fiber. A bundle of optical fibers is called light pipe. This pipe can transmit an image, hence it is used for medical and optical examinations of even the inaccessible part of human body as an endoscopy. Yes, endoscopy is the technique by which light signals are entered in our body. So that is carried out with the help of optical fibers. Optical fibers are used in telephone and other transmitting cables. Each fiber can carry up to 2000 telephone messages without much loss of intensity. So this is complete about optical fiber communications. Okay. Now we are talking about mirage. What is mirage? Mirage means like of illusion. In the summertime, you have seen when you are in a car or some vehicle, you have seen there is a sensation of water in the roadside, on the roadside. Okay. But actually, there is nothing. So why it is happening? Actually, see, this is a big tree. Okay. A tree is there. Now, the during the summers, the intensity of the refractive index of the air continuously decreasing. Okay, yes, check. Situation is like this. Here it is a tree. Now there is a huge layer of air. Okay, above side the temperature is less, so the here the air is dense, and here the air is rare. The medium to near the earth is rare because earth is warmer in the time of summer. Clear? Now the light ray is coming from the denser medium to the rarer medium. Let's see what happening. These rays, light rays coming traveling from the tree continuously bending towards the normal. Clear? So they are bending towards the normal. At some place, the light rays coming bending towards the normal, denser to rarer. At some place, there will be totally internally reflection, and the totally internally reflection will takes place, and the light ray continuously getting away from the normal. Now, if the light ray entered towards the eye of the observer, he will see the virtual image of the image, which like this here. Okay. Yes. Due to the air, if the leaves of the plant are shaking, okay, then here also a virtual image of the plant leaf here is looking like moving moving leaves. Clear or not clear? It is nothing but illusion. Okay. So this is the virtual image. In this place, there will be a virtual image of the plant, of the tree, and the observer have a sensation or having a illusion that there is a water, because only water can make a image of this one plant. So he thought that there is a place of water, but it is not. Now read this one. Yes, it is the phenomenon in which inverted image of the distance tall object cause an optical illusion of water. This is type of mirage especially in common in hot desert. On hot summer days, the air near the ground becomes hotter than air in higher levels. Hotter air is less dense and has a smaller refractive index than cooler air. The optical density at different layers of air increases with height. Yes. So optical density of the different layers of air increases with height. The light from a taller object passes through a medium whose refractive index decreases towards ground. Thus, light ray bends away from the normal and undergo total internal reflection. So, what happening here? Here, density is high, and here density nearer the ground is low, as the warmer air is there near the ground. So on going from denser medium to rarer medium, at some place there will be total internally reflection, and the light ray is will go reflected that, and the observer will found a image, virtual image of the object as a result of totally internally reflection. Thus, light from the tall object passes through the medium whose refractive index decreases towards ground. Thus, light ray bends away from the normal, undergoes total internal reflection. Clear?